Today I'm going to speak about the anisotropic calculus. In some sense, we will speak about the tools to study the main elements of Finsler geometry. So, well, the basic idea is to see how to handle the anisotropic tensors and curvature. Everything here depends on direction. So we have to choose some tools in order to handle with this isotropy, with the dependence on direction. So let's see which are the main elements of Finsler geometry. Probably the most important element in Finsler geometry is geodesics, which are the curves that minimize the length, at least locally. Then the flat curvature, which is a measure of how geodesics get apart. And then, of course, as in Riemannian geometry, we want to choose a good connection in order to make computations. And well, in this case, the problem is that there is a dependence on direction. For example, remember that we can define the fundamental tensor, which is a very important quantity, and basically is 1/2 of the Hessian of the square of the Finsler metric, and this provides a scalar product for every direction. There is a dependence, a strong dependence on direction. So at the end, we obtain a sea of tensors. There are many tensors with which depend on the direction. So it is not easy to make computations in this context. Okay, and probably this is the reason because a big part of the Riemannian community doesn't like to work on Finsler geometry. So in this talk, we will try to put some order, and we will see how to make computations in such a way that it is not so complicated. So let's go to define anisotropic tensors. So we have a manifold, and for every direction, and we will define a multilinear map in such a way that it is defined in a product in a product of R terms of the cotangent space and S terms of the tangent space. Okay, we have this product. This is a multilinear map, and here, well, probably the most important thing is that this V here, this small v, it is the same. It is in the space where these tangent and cotangent spaces live. I mean, no, this V lives in this tangent space. Okay, belongs to here. So this tangent space in the point where this V projects, the natural projection falls. So, well, when we have this tensor, I mean, the idea is that in comparison with Riemannian geometry, in manifolds, we work with, we have a tensor, a multilinear map for every P. At every point, we have a multilinear map. To have a tensor, a field of tensors is to choose in a smooth way a multilinear map for every P. In this case, we will choose a multilinear map for every V in the tangent bundle. Okay, so there is a dependence of the tensor on the direction. Then we can, when we have a system of coordinates, a chart, then we can define the coordinates of this tensor. And these coordinates, of course, in this case, will depend on the direction. How we define the coordinates? Exactly as in the isotopic cases. We put the tensor in the differential of the functions and in the partial of the function. Of course, the tensor is smooth when these coordinates are smooth. Okay. moreover, so this is exactly the same as in the classical case. The only thing is that there is here a dependence is in the direction rather than in the point. Then we also can identify Dynastopic vector fields with the tensors of type 1, 0, with this type of tensors. Okay. Well, the first thing, what is an anisotropic vector field? Is a vector field, is a map, let's say that is a map from the tangent bundle to Tn in such a way that for every v, the image which is in the tangent bundle is also in the same space as v, as small v, okay, in the same tangent space. So for every direction, we assign another vector field in the same space. Okay, this is an anisotropic vector field, and well, this can be identified with the tensors of type 1, 0, the same way that in the classical case, the smooth vector fields are identified with tensors of type 1, 0. So the next concept that we will need is the concept of anisotropic connections. And this is something very, very similar to the classical affine connections. But there will be a dependence on directions. It is what I want to say is that here we will have a map. A is a subset or is an open subset. A is always a subset of the tangent bundle minus the zero section. Okay, we have to exclude the zero section. And then for every pair of vector fields x, y, we define nabla. We define nabla xy in V in this way. We, in order to have an anisotropic linear connection, there are several properties that it has to satisfy. Okay, and these properties are pretty much the same as in the classical case, because it has to be linear in the second component in y. So it has to be linear in y. It must satisfy the Leibniz rule, okay, with respect to functions in f of n. Well, here it's important to remark that we are considering isotropic classical vector fields. I mean, x and y are classical vector fields at this stage. Okay, are classical vector fields. So here the function f is also a smooth function on the manifold, not in the tangent bundle. Okay, so for every v, we have to this connection, this anisotropic connection, has to satisfy the Leibniz rule. And then has to be linear also in the x component. Okay. And finally, maybe these three conditions are the same as in the classical case, but there is a fourth condition, which is that has to be when vary v, the vector v, because for every v we have a different value, the condition, and then in fact, when we vary small v, we have an anisotropic vector field, and it has to be smooth. Okay, this is the condition of smoothness. Okay, well, in the classical definition of anisotropic connections, affine connection, you don't have to use that. This connection, is smooth, because in fact, in the definition, in the classical definition, you put here x and y. So, sorry, you put here this, which means that directly there is no, of course, in the classical case, there is no dependence on the direction, and nabla xy by definition is a smooth vector field. So in this case, well, the analogous property is that this has to be, this anisotropic vector field has to be smooth. Okay. In fact, here I could define this putting here tensors of type 1, 0, m. Okay, and this in fact would be the same as to state the fourth default property. Okay, so but well, summing up, an anisotropic connection is something very similar to affine connections, but there is a dependence on direction. Well, in the same way, we can define the torsion tensor. Is basically the same formula as in the classical case, but with the dependence on the direction. Moreover, we will see that an anisotropic linear connection is torsion-free if the torsion tension is 0. And the torsion tension is 0, it means that the connection, let's say that the Lie bracket is equal to the nabla xy minus nabla yx. Okay. So we also can define the Christoffel symbols. The Christoffel symbols are defined exactly as in the classical affine connections. Is we have to express nabla on partial j, partial k as a combination, as a linear combination of the partials of the coordinate system, and the coefficients are exactly the coefficients of this linear combination are the Christoffel symbols. So it turns out that when a connection is torsion-free, if and only if the Christoffel symbols are symmetric. Maybe the main difference here is that the Christoffel symbols are functions on the tangent bundle, on an open subset of the tangent bundle, whereas in the classical case are functions in the manifold. Okay. Finally, we can also define the autoparallel curves using these Christoffel symbols. Just as in the classical case, the only difference is that here in the Christoffel symbols, rather than only gamma to put gamma, the curve, we have to put the derivative of the curve. Okay. So this autoparallel curves can also be defined using a covariant derivative. Basically, you can use a covariant derivative along any curve, using, of course, the affine connection. You can use this using also the Christoffel symbols in a system of coordinates. And then the autoparallel curves are given by this equation here. Okay. In any case, these curves are defined for every direction. When you fix the initial value, the initial velocity of these curves, then the curve is determined. Okay. Here, I'm not assuming that the connection are homogeneous. I mean, in particular, this Christoffel symbols doesn't have to be homogeneous of degree 0. In the case of the Finsler or pseudo-Finsler metrics, these Christoffel symbols will be homogeneous of degree 0. Okay, but at this stage, I don't need homogeneity. And using this affine connection, you can define a covariant derivative. You can define a covariant derivative, and then you can define formally this expression here, the derivative of a curve, okay, and the autoparallel curves. So we have the anisotropic connection, and we can define autoparallel curves. That in the case when this anisotropic connection comes from a Finsler metric, will be the geodesics. Okay. So, well, let me introduce a spray because it will be important in this presentation. So, given a manifold, a semi spray on M is a vector field S in a subset A in the tangent bundle with the following property: the integral curves of S are of this form. Are the derivative of a curve in the manifold, the projection of this curve in the manifold. Okay. Well, moreover, if this family of curves, is in some sense, these curves alpha are invariant by affine reparametrizations, then the spray is the semi-spray is a spray. Okay, and this is the same that this property here. Yeah? This property means that these curves alpha are invariant by a fine, not invariant. I mean, it remain. What I want to say that they remain in the spray. They are also a solution of the integral curves of the spray of S. Okay, so this is a very general notion of spray. So, well, the point is that, well, in coordinates, a spray can be expressed in this way, okay? In the natural coordinates of the tangent bundle, we consider the natural coordinates, and then it turns out that the first coordinates at determined are always in this way, and then there is a gauge, there is a freedom in the last coordinates, and these coefficients are called the spray coefficients. These are the spray coefficients. Well, if we have a spray, these coefficients are homogeneous of degree 2, and then in this case you can define these Christoffel symbols here. These Christoffel symbols are basically the second partial derivatives of the coefficient of the spray. Okay, are the second partial derivatives. It turns out that with these coefficients you can define an isotopic connection, which is the Bernoulli connection of the spray. So every spray can be defined using the Bernoulli connection, because it turns out that autoparallel curves of this Bernoulli connection are the integral curves of S. Okay, so if we want to study sprays, then it is enough to study anisotropic connections. Okay, or in this case, the anisotropic connections are homogeneous in D. Okay, I mean, here, let me go back here. It means that here, when you put lambda V, this is going to be homogeneous to degree 0. It is the same. I mean, sorry. Yeah, what I mean is that this is equal to this. Okay. But yes, this happens for the sprays, and it will happen also for Finsler metrics, for the connection associated with Finsler metrics. But in this first part, I don't need it. Okay, so, well, we have the spray, we have the Bernoulli connection, which is an anisotropic connection defined in this way. So, well, let's say how to make derivatives with an anisotropic connection. Okay, we want to consider an isotopic tensor, and then to make the derivative of this anisotropic tensor. Okay, so the first observation here, well, I mean, you can assume that A is equal to the tangent bundle minus the zero section, but we can consider a much more general case. Okay. Well, here, the first thing that we are going to do is to associate an affine connection with the anisotropic connection. And this can be done whenever you fix an A-admissible vector field V. A-admissible V, that the values of V are in the subset A. So for every P in M, VP belongs to A. Okay, this means A-admissible. So when you fix this vector field V, then you can define an affine connection nabla V, just making this definition. Okay, because here, when you have an anisotropic connection, here you can put the vector, whatever vector. So in particular, in P, you put here V on P. Okay. So, well, when you fix a vector field, and on this A-admissible vector field, you have an affine connection. Okay, this is the first observation. This will be very important for my approach. Okay, then you can define the vertical derivation. The vertical derivation of a tensor is just to make the derivative with respect to the direction. Okay, here in this derivative, all these vectors are constant, are fixed, and you make the derivative only in this component here in the direction. Okay, because in fact in this derivative you are moving in the fiber of the tangent bundle. This is because you call it vertical derivation, or you can say also fiber derivation. Okay, so we have these two elements which are very important in order to define the derivative of an isotopic tensor. So now let us consider the anisotopic functions, which are functions, just functions on A. Okay, it is contained. I recall that A is contained in Tn minus the zero section. Okay, so well, the first thing that we are going to do is to define the derivative of this of an isotopic function, the derivative of this function here, with respect to a vector field, but is a vector field Z is a vector field in the manifold. Okay, so in principle this is not easy because look, this function is defining the tangent bundle, and this vector field is in the manifold. So it is not, in principle, Z that does not apply to H. Okay, but we are gonna do the definition in this way. Observe that if you consider a V admissible extension of small v, so capital V is an extension of small v. This what means is that capital V takes small v as a value. Okay, then Z can be applied to this function. That this function, this composition here, is a function in the manifold. Okay, so you can make the derivative of this function with respect to Z, and then you subtract. But this depends on the choice of V or capital V. V is an arbitrary choice, or an arbitrary extension of small v. So this term here depends on this choice. But then if you subtract the vertical derivative of this derivation, evaluated in this derivation, which is to make the derivative using the anisotropic connection of V, of capital V, with respect to Z, then it turns out that this does not depend on the choice of V. So we can, in some sense, define the derivative of anisotropic functions in the tangent bundle with respect to vector field in the manifold. Okay, but this is because we have this anisotropic connection. Okay, so this is the first lemma. You can find the proof in this paper here, which from now on, this paper here, that from now on will be JAP 19. Okay, so we know how to make the derivative of anisotropic functions. We know, of course, we also know how to make the derivative of vector fields with the anisotropic connection. So now we want to make the derivative of arbitrary anisotropic tensors. So what we want to do is to define a tensor derivation. A tensor derivation is a map, our linear map that goes from the union of all the anisotropic tensors to the union of all anisotropic tensors, preserves the type of tensor, and satisfies the Leibniz rule for the tensor product. And also it commutes with contractions. So it turns out that if we have an anisotropic connection, there is a unique tensor derivation. It is uniquely determined, such that in nabla x, this is for every x in the vector field in the manifold, there is a unique nabla x such that when it is applied to vector fields, it acts like the anisotropic linear connection, and in functions is defined as before, as in the lemma. in anisotropic functions. Okay, so this is a theorem also in this paper here, and well, if with this you can define the derivative for every arbitrary tensor, an isotopic tensor. So how can you do that? Well, you have to use the product rule. And using the product rule, if you take a tensor of type 02, it is very easy to obtain the formula for the derivative. This is the derivative, and you can evaluate the derivative, and you obtain this. This formula is very similar to the classical case of isotopic tensors. Okay, it is the same. It is the same. Well, there is a trick here, because this first term, it is, well, in the classical case, you write this, because in the classical case, this is a function on the manifold. In this case, it's not. It's a function on the tangent bundle, because there is a dependence here on the direction. So we have to compute this. Okay. How you compute this? Using the lemma. And using the lemma, you obtain two terms. Okay. So now we can compute the formula for the derivative of the tensor T. Okay. What is new here? Well, very important. We can make the computation using only this affine connection. This affine connection, and then also the vertical derivative, the two elements. Okay. We have to choose an extension vector field V, but this definition does not depend on the extension of V. Does not depend on extension, and everything can be done with an affine connection. And this is the key point. I mean, which is new in this approach, is that you can make all the computations using an affine connection. Okay, so well, we have the definition. We have how we know now how to make the derivative of tensors, and now the next point is to obtain the curvature tensor. Okay, and in order to do that, first we need to make the derivative of an isotopic tensor, an isotopic vector field. Sorry, because well, when we have defined an isotopic connection, we have done that only for classical vector fields. So what happens if I put here an isotopic vector field? Well, I can express this vector field in a basis in a system of coordinates, and then these are classical vector fields, and these are functions which are anisotropic functions. Then I can apply the lemma in order to make the Leibniz rule, and then the lemma to make the derivative of these functions, and it turns out that I obtain this formula here. Okay, so at the end, well, I have a formula for the derivation of anisotropic vector fields, and then using this, I can define the curvature tensor. And the expression of the curvature tensor is the same, exactly the same as for affine connections. So, but again, here, well, here there is a difference. The difference is that this vector here, this pink vector, is an isotopic vector field. So I had to apply this formula here in order to compute it. In such a way, I obtain this relation here. Okay, and it appears the vertical derivation of this connection. So finally, if I define the vertical derivative of the anisotropic connection in this way, just is two x and y are constant, and then I vary only the dependence on the direction, then I finally can express the curvature tensor in this way. And again, it is expressed in terms of the affine connection nabla-V. Everything depends on an affine connection. Okay, this is an RV is an anisotropic tensor. Well, this is the way to define the curvature tensor of an anisotropic connection. Okay, well, a very important thing, we are doing everything in terms of this anisotropic connection. So and this anisotropic connection, in order to obtain this, we have to make a choice of V, or of capital V. Okay, and this is arbitrary. It doesn't depend on the choice. Okay, so we have to to use this. We have a lot of freedom in this choice. So which is the best choice? Probably the best choice is this one. To make a choice in such a way that when you make the derivative of v, this is equal to 0. Because in this case, if you make this choice of the extension v, then when you make the derivative of a tensor, it is the same thing that making the derivative with respect to the connection nabla v, okay? But only in this point, okay? Because I mean, this can be done, this choice can be done, but only for the point. I mean, this is 0 only in this system v, in small v. It's not, it cannot be 0. I mean, in general, it's not 0 in a neighborhood of v. It's 0 only in this point, okay? So, well, in order to compute the curvature tensor, this is very nice because the curvature tensor is the tensor of the connection nabla v, okay? And it even can be reduced more if you make this choice. No, this is always, this equality here is always true. This is true whenever you make this choice here, okay? So far so good. What happens when you make the derivative of the tensor? Well, in this case, you will obtain extra terms. Why? Because here you have to make the derivative of this term here. This term here, this term can be 0 in a point, but not in a neighborhood. So when you make the derivative, maybe it's not 0. So in this case, the derivative of the curvature tensor is the derivative of the curvature tensor of RB, of the affine connection, plus or minus some terms, okay? So we can use all these relations to obtain, for example, the Bianchi identities. And this is, the first Bianchi identity is immediate, just using that you have this nabla connection, and the curvature tensor is the same as for the nabla v connection, and then you use the first Bianchi identity for the affine connection. Well, in the second Bianchi identity is a little bit more difficult because there are extra terms, but you can use this relation at the end. It appears an additional term. Okay, so you have basically the first and second Bianchi identity almost for free with this approach. And then you obtain a new vertical Bianchi identity that basically depends on the vertical derivative of the anisotropic connection. Okay, there are many times appear this tensor. So well, these results are in this other paper, which from now on will be JAP 20. Okay, so let's go back to the Finsler world, Finsler realm. In the Finsler realm, I recall that we have a fundamental tensor and a Cartan tensor, and these are anisotropic tensors. Okay, so it is very easy to see by the definitions that the vertical derivative of the fundamental tensor is twice the Cartan tensor. And then it is immediate to check that if you take any anisotropic connection, the derivative of G, it is computed in this way. Okay. So what happens if this derivative is 0? Is the case of Levi-Civita. Levi-Civita connection, it is characterized because it's torsion free and the derivative is 0. It's compatible with the metric, means that nabla G is 0. Well, but in this case, this is equivalent to these two equations, and it is well known that this is the chair connection, okay? Because this basically is Levi-Civita connection. So chair connection from the viewpoint of an isotropic calculus is Levi-Civita connection of the Finsler metric, okay? So, well, this has been developed. I mean, the first ideas were in the thesis by Matthias, using a family of affine connections to study Finsler geometry, to study chain connection. Then I discovered this here in this paper by Rademacher, but it also appeared in a book by Shen. But well, here it is there there is no definition of the derivative of a tensor. Okay, they were using this in a more basic way. So I don't have much time, so I'm gonna skip most of this. But basically, well, this started with the study of the osculating metric GB. Okay, then well, Varga realized that when you take a geodesic vector field, V is a geodesic vector field, and there are some properties about geodesics, and then well, Shen Matthias used these term connections, and Shen realized that the Jacobi operator of this nabla has the same properties as the chain connection. Okay. So, well, let's see the relation of these anisotropic connections with the classical connections used in Finsler geometry. In Finsler geometry, the classical connections are connections in the vertical bundle. Okay, the vertical bundle is just the tangent space to the fibers of the tangent bundle. Okay, it is formed by the vertical vectors of the tangent bundle. Okay. So, well, a classical connection is a connection in the vertical bundle, and it is a map this way. Okay. So, well, the main point here is that you take derivatives with respect to vectors which are tangent to the tangent bundle. So you have to use a system of a charge in the tangent bundle, which is this way here. And then it turns out that there are two types of Christoffel symbols. You can take the derivative with respect to the partial vectors which are of this type, or with respect to the partial vectors of this type here. So in anisotropic connections, we have half of Christoffel symbols. Okay, half of Christoffel symbols. There is a simplification in some sense. So, and how to construct an anisotropic connection from this classical connection? There is a very good relation between them. So the first thing is an observation is that when we have a Finsler metric, it is naturally defined a horizontal space in the tangent bundle. Okay, in the tangent to the tangent bundle. So, and then you can make given a vector field in the tangent in the manifold, you can make the lead to a horizontal field in Tn. Okay. So then you also can make an identification between the tangent space to n and the vertical space to Tn, just well, in a trivial way. So you can also make the vertical lift. You have a horizontal lift and a vertical lift. So we can define an anisotropic connection in this way here. Okay, we have x, we consider the horizontal lift, and then y, we also always consider the vertical lift. Okay, and an anisotropic, there is also an anisotropic tensor associated with the classical connection. Okay, and this anisotropic tensor is just rather than consider here the horizontal lift, we can consider the vertical lift. So these two quantities here, the anisotropic connection and this anisotropic tensor, describe all the properties of the classical connection. Okay, so let's see the relation between these classical connections and our anisotropic connections. So the first one, the Chern-Room connection, which is what we have called Levi-Chita connection, projects into Levi-Chita connection, and then this tensor here is 0. Okay, the C tensor is 0. Then we have a Cartan connection, which also projects. I mean, the first anisotropic connection is Levi-Chita, is the same one, and the tensor C is constantly from the Cartan tensor. Okay. Then we have Bewald connection that projects into Bewald connection, and the tensor C, this tensor C is 0. And finally, Hasibuchi connection projects also into Bewald, and this other tensor is constructed from the Cartan tensor. Okay, you have all the details here in Jap 20. And well, let's see the relation between, we have defined so far two anisotropic connections. So let's see the relation between these two anisotropic connections. Basically, when you have the Beer-Wall connection, you have the Beer-Wall tensor is the vertical derivative of the Beer-Wall tensor. And then from the Beer-Wall tensor, which is the vertical derivative of nabla 2, you can define the Landsberg curvature. The Landsberg curvature is defined in this way. And well, just multiplying by the position vector the Beer-Wall tensor. Okay. Then if we define this Landsberg flat, let's say, which is metrically equivalent to the Landsberg tensor, the difference between Chern and Beer-Wall is this tensor here. Okay, this can be found in this book by Shen, Differential Geometry of Space and Finsler spaces. And well, as a consequence, you can prove this property for the derivative of the Chern connection. Okay, this is a technical thing. Well, it turns out that when the difference, Landsberg flat had this property. When one of the components is the position vector, then this is 0. If the difference of two connections has these properties, this difference has this property, then the connection is good. Difference between Beer-Wall or Chern connection with this new connection has this property, then this connection is going to be good, nice to study Finsler geometry. So, turns out that there are many connections that can be used to study Finsler geometry, in the sense that you can compute geodesics, you can compute the flat curvature, and so on. So let us see the properties of the curvature tensor. Now we have two anisotopic connections associated with a Finsler metric, a pseudo Finsler metric, which are Chern and Beer-Wall. We are going to see the properties of the Levi-Civita-Chern connection. Right? It's the Chern connection, but I call it Levi-Civita-Chern because nabla G with my anisotropic calculus is 0. So, well, the first property, these are the symmetry properties. Well, here, if you interchange U and W, it is antisymmetric. It changes the sign. But if you change these two vectors, then it appears a term here. Now, if you change these two vectors with these two, well, it appears many terms. Okay, there are 6 terms here. Okay. Well, so let's go to the main thing of all this calculus, which is the flat curvature, because this is the most important invariant in Finsler geometry. And this is defined using the curvature, curvature tensor, and here you can put the curvature tensor of the Chern connection or the Beer-Wall, and at the end it coincides. It's the same, and all of the other connections that I call distinguished connections, which are good for Finsler geometry. But just to fix ideas, we are going to assume here that this curvature tensor is computed with the Chern connection. Okay, and this measures how geodesics get apart from the initial geodesic V in the direction V. This maybe it is better to write this because, to put here the V, because the V is the flat pole. It is important. This is the reason, because it's the direction V of the geodesic is the flat pole, and then you have here the flat. This is the main reason, because we call it the flat curvature. Okay, because this direction here is very important. The flat pole is very important. So, well, the interpretation of the flat curvature, this is a picture in this book, in this very classical book by Bao, Chern, Shen. And, well, this U is a Jacobi field, and then basically the flat curvature is measures how these geodesics get apart. So this is the tangent space, what happened in Rn, let's say. And then when it is positive, geodesics get apart slower, okay? And when it is negative, geodesics get apart faster than in Euclidean space. Okay, because this is the flat curvature appear here when you compute the norm of this Jacobi field. Okay. So, well, there is no classification of Finsler manifolds with constant flat curvature. That's very surprising. There is only one known case, which is the family of Randers metrics. There is a classification, and this classification was done using the Zermelo data. Zermelo data, remember that the Randers metric, the indicatrix of the Randers metric is the translation. It is the translation of a Riemannian metric. So this is the Riemannian metric that you translate H, and that W is the wind used to translate this Riemannian metric. It turns out that the Randers metric has constant flat curvature, if and only if H has constant curvature and W is a homothency. Okay, so well, Zermelo problem appears here in a very, very nice way. So, well, let me just mention that you can also define the leader derivative using all these machinery with tensor derivations and so on. And, well, you have a very similar formula to the lemma that we use to make the derivatives of anisotopic functions, and then you can define you can obtain the derivative using the chain connection, because the chain connection is related to the Lie bracket, and you can also characterize Killing field as with this equation, conformal fields, and so on. You can make the derivative of the fundamental tensor. You can express this derivative in terms of the anisotopic connections. But probably the most interesting of this Lie derivative is this formula here, this proposition. This happens in the case of the Lie derivative in the tangent bundle. This is an extension of the classical Lie derivative. Okay, because here we are making the derivative of anisotropic tensors, and it turns out that this derivative is measuring the derivative of the flow of the anisotropic tensor in some sense. Okay, the flow with the vector field x, the flow of x. Okay, so if this tensor t is constant along this flow, then this derivative is zero. Okay, so let me speak in the last minutes about some manifolds of a Finsler manifold. Well, in this case, you can, when you have a submanifold, you can induce the Finsler metric in the submanifold with this restriction. Then you have at the chain connection of the Finsler manifold and the chain connection of the induced metric. You have two chain connections. But there is another anisotropic connection, which is the tangent part to the chain connection of the ambient manifold. Well, then you can define the second fundamental form of the submanifold using this. This is the orthogonal part using GV to compute the orthogonal part, and then the tangent part. But in this case, the chain connection of the submanifold does not coincide with the tangent part. These are different. These two anisotropic connections are different. So you have to introduce a tensor, the different tensor that, well, has many properties that, well, it is basically is determined by this relation here. And, well, the important thing is that it can be determined. Okay, it can be determined, this tensor Q, which is the difference between, this is the tangent part of the chain connection of the ambient manifold, and this is the chain connection of the submanifold. Okay, so, well, now we can obtain the Gauss equation of the submanifold. Okay, this is the Gauss equation. This is not new. It appeared in many papers, beginning from Heimovich in 35, Homo 36. But we have seen a version using anisotropic calculus in this paper here, collaboration with Mathieu Huber, which is for now is HJ20. And well, the important thing here is that, well, in fact, in this, here, I put the curvature of the tangent part. This is not the curvature of the chain connection of the submanifold. So if you want to express the Gauss equation in terms of the chain connection of the submanifold, then you have to use that when you have the curvature tensors associated with two arbitrary isotopic connections, you can obtain this relation between the two curvature tensors. Okay, the formula is huge, is very big, but it turns out that when you compute the flat curvature, there are a lot of cancellations, and well, the final formula is this one. The final formula is this one. And look, the first part is the same as in these two terms here are the same as in Riemannian geometry, and then it appeared three terms. This one here, this other one here, it depends on Cartan, and this other final term. Well, if the ambient manifold is a Minkowski space means that you have a vector space with a flat metric in the sense that it's the same metric in all the points of the vector space, then this is zero. This is zero in Minkowski. Okay. So, well, I haven't seen this formula. In the papers. I'm not sure if there is this formula in the other. I mean, in all these papers, because I haven't checked all the papers. But in many of them, they don't compute this relation between the flat curvatures. Okay, but our main contribution is to compute this flat curvature in the case when you have a Randers Minkowski space. That means it's a Minkowski space. The metric is flat, and is of Randers Minkowski type. H is, let's say, the Euclidean metric, and W is constant vector field. In such a case, when you compute the flat curvature, at the end, the flat curvature, it is expressed in this way. This is the sectional curvature of H as a Euclidean manifold, as a Euclidean submanifold, and then, well, this is the second fundamental form as a Euclidean submanifold. So everything here, everything in this formula, there are many terms, but everything is computed in terms of the Zermelo data. And look, all these terms here depend only on V, on the direction. There's no dependence on U. And this is more clear even when you take a hypersurface. If you consider hypersurface, well, all these terms here depend only on V. There is only one term with a dependence on U. So it is very easy to construct submanifold which have a scalar curvature. Scalar means that the curvature depends only on V. Depends only on the flat pole. So it is a function on the tangent bundle. Okay. So just comment about how to obtain all these formulas. Well, how can you use anisotropic calculus in order to make these computations? In order to obtain this formula of the Gauss equation, the key point is this condition here. You can choose. Recall, we want to make all these computations with affine connections, and in this case, we have to make an election such that this is equal to 0. Okay, we make the election of V, capital V, in this way. Then you cannot ensure that this is 0 for the ambient space, but for the ambient space, as this is 0, this is gonna be equal to nabla B XV. Okay, so with all these, here in the anisotropic calculus, it is very important how you make this choice here, the choice of B. You can make any choice you want, okay? But in every case, it is convenient to make a different choice. It's like when you want to make computations in Riemannian geometry, you usually choose vector fields such that the Lie bracket is 0. Okay. Of course, you can also do this and make this choice in this case. Okay. So in this way, you simplify all the computations, and well, you can make all these computations without using coordinates. There is no, basically, we don't have any coordinates to make this computation. Okay.
Sorry,
So,
Miguel Angel.
well,
I was wondering whether you would find a good point to stop, because we are running over time.
I'm just in the last slide.
Very good. Just making sure that we don't go over time.
Yeah, well, here I just want to make, we have seen that there are applications, for example, to compute Gaussian equations. We can compute explicitly the flat curvature as a manifold. This is something, for me, very surprising. I didn't expect that we would be able to make this computation. We can do this for a Finsler some manifold in order to compute the fundamental equations of O'Neill, and this also can be used. These equations can be used in order to study Lorentz-Finsler spacetimes, because we have the Einstein equations, and then we can study the solutions. And classically, you use the Warper products and summations in order to compute the curvature. Okay, and also the final application can be to study the classification of Finsler manifolds with constant flat curvature. So I stop here. I remember that we have these main references. And thank you very much for your attention.